Sorry, anyone is saying something?
Yes, do you know what the average for the midterm was, or any of the questions?
Let me take a look. On the grade scope, I think. The mean is 6.9. Yeah.
Okay, thank you.
Okay, whatever. So, uh, right. So let's start today's discussion. Today we will talk about complex numbers. And also I prepared some, first we will go through some points I think that you need to know, then we do some examples. So first thing I want to say is about the motivation. Of course, let's talk about physics. Uh, so for quantum physics, here's just some backgrounds. Quantum physics. The complex number is a must for quantum physics because we know that the basic Schrodinger equation like this, there's a complex numbers and you so complex number is a must for uh, quantum physics. And here I show you two pictures I took from my quantum books. Also, this left one is from quantum mechanics book. You can see there are some complex numbers here. And also this kind of x in general is a complex matrix. So you can regard a complex number as a special case of a complex matrix, right? So or you need this kind of complex number, complex functions. And the right one is a book from about quantum field theory. You can also see there's some complex numbers, complex integrals. Just show you if you open up to quantum book, you will see many complex numbers, and yeah, that's unavoidable for quantum mechanics. So for classical mechanics, classical or classical mechanics or classical problems, so complex number is not necessary, but it can help you to simplify your calculation in many cases. So there is a one example I think is also in the textbook. uh, imagine imagine you have a you have a spring connect with the object and it's oscillating. Of course, we know the equation of motion is given by F equal to ma, right? So F, the force in this case is the spring force minus kx, and you write down the equation of motion, the dynamic equation, which is something like this. And in using the real numbers, of course, so we can solve this x like as a times sine omega t plus b times cosine omega t. The frequency here is just the square root of k over m, right? This is what we did in, I think, in 1A or, yeah, 1A or 1B. 1B, yeah, small oscillations in 1B, I think. Of course, you can write this kind of a solution in in this way. So A here, B here are unknown parameters. A tilde and phi here are unknown parameters. They are fixed by two initial conditions. One is the initial position and another one is the initial velocity, right? So basically, there are two unknown parameters. In your solution. the corresponding the reason why there are two unknown parameters is because your equation motion is kind of a second order derivative of time. And this corresponding to you must give me two boundary conditions to determine the solution. Basically the initial velocity and the initial initial position, right? Yeah, this is how we solve this problem using real numbers. Of course, we can solve this using complex numbers. For example, because we know that we can assume this x is in the solution is in this form, and omega similarly is a frequency determined by this. So here x naught in general is a complex number or something like this. Yeah. C, this kind of a C stands for complex number. And so if we write x naught as the A exponential I phi, we know that this is a polar form of a complex number. Then we get A exponential I omega t plus phi. So the only physical part of this solution is a real part of this, which is given by A times cosine omega t plus phi. This is our solution. I mean, it doesn't matter whether I use the sine or cosine. You can also use cosine, yeah. So basically, for classical problems, we usually can solve it using complex numbers or using real numbers. Sometimes complex numbers will simplify your calculation or not. Okay, so any question about this example? So okay, okay, this is just a motivation. So why complex number is important for physics at least. So then I'll go through some important points you need to know about complex numbers. So the first one is about the two different forms. For complex number in general, you can write it as x plus iy. So here x, y are both real numbers. And also you can write this as the polar form, which is I phi. R is a number from 0 to infinity. And the phi, usually we set it as is from 0 to 2 pi, right? By the way, just feel free to stop me and ask me questions. Yeah. Also, you just need to unmute yourself and speak out. You don't need to yeah, type in the chat. It's easier for me to answer your question, I guess. In principle, of course, you can say, okay, I say if I allow omega, sorry, phi to be a general from minus infinity to infinity, but the only real effective part is the 0 to 2 pi, right? Because like, for example, I have a I5 pi, but we know that this guy can be written as I4 pi. This guy is 1. So yeah. You can always restrict your pi to this regime. Okay, so this is for the complex numbers, and the second thing is the geometric meaning. So first, so when we write down a complex number, we usually say it's a point in the complex plane. For a complex plane, we draw x, y. Like for example, if this is x, this is y. right? So this point is x plus iy. And also you, in terms of this pointer form, this is r, this is theta. So this picture tells you the relation between x and r. So x, y, and r theta or r phi. So basically, this is x. So x equal to the r times cosine phi. This is y equal to r times sine phi. Right? What else? So okay, so another thing is the complex conjugate, which is just by the way, this is actually a very important operation. Uh, you flip the sign of I, right? Meaning that this, if this is Z, then the Z bar is here. They are kind of symmetric around the x-axis. Basically, they have the same x coordinate, but opposite y coordinate. Y, this is -1. And another thing that you need to know is the meaning of the minus D naught. Okay, so this correspond D naught, both D and Z naught are complex numbers. So for example, this point is the Z is Z. Yeah, let's call it Z. And the Z naught is also another complex number. Let's see, let's call it X naught plus IY naught. This guy is X plus IY. Then this expression stands for the distance from this D naught to the D naught to the point Z, right? So basically, this is the reason is also quite simple. You can because this guy, you know, according to the definition, what's this? This is square root of Z minus D naught times the Z minus D naught conjugate, right? If you write down this expression, plug in, you will get is given by x minus x1 squared plus y minus y0 squared. Basically, this is the definition of the distance from this point to this point. One special case is when z equals 0. Basically, you have z minus z. So you get z absolute value. You can understand this guy as -0 plus I0, right? So this stands for the distance from the point Z to the orange. This is nothing but the R, right? Of course, Z is exponential I theta, so I phi. Sometimes use theta, sometimes use phi, it doesn't matter, it's just a symbol. This is R, right? Yeah. Because exponential I phi is always 1. It's just a phase. It's a phase. The magnitude is 1. And we know that R is always a non-negative value. So the absolute value of R is always R. So yeah, any question about this part? Like this part? I hope it's clear. It's clean now. Okay, so the next thing I want to say is about the function of a complex number. Basically, usually when we have a function and the argument is a complex number, it's usually defined using the Tanner series or series, which is this. Oops. Some coefficients. I don't know. And something like this. Yeah. And one important example is the exponential of z, which is, we know in the real calculus, we know this guy, if x is a real number, we know the Taylor series is given by this, right? So similarly, this guy is also given by, given by what? Yeah, given by this. Dm. And even if this guy is we can generalize this kind of complex number to a matrix. For example, 2 by 2 matrix, Z1, Z2, Z3, Z4. In general, Zi, like Z1, Z2, Z3, Z4, they are all complex numbers. I denote as X. Then this capital X is also defined in this way. So here, instead of a number multiplication, here, this xn, for example, n equal to 2, so x squared is x times x. Here is a matrix multiplication, right? So this is what I showed you in the first picture here. Oops. You can say here x in general is a complex matrix. It's always defined by this kind of a series, like Taylor series. You can think of this complex number is just a special case of this matrix form. Yeah, you can think of a complex number as a 1 by 1 matrix, right? Let's add another page. Yeah. So by the way, once we have this kind of exponential z, we can define sine z, right? Sine z, because sine z is defined, and we can decompose sine z and like I think it's something like what's this or something like that. Cosine z is 2iz plus minus z. And we can also define the sinh and the coach. I actually didn't remember. I think it's something like this. Yeah, whatever. You need to double check. Yeah. I'm not sure about this. So anyway, if we have this, we can actually prove the relation we used before, like the relation I wrote down somewhere here. Yeah. Yeah, basically, basically exponential I theta. I use the use this one, cosine 5. Okay, so if I sine 5. I use this equation equality. We can prove this equality using the series here. Basically, you can write it down using the definition. So definition is given by this. And then we consider two cases. When n is a even number, basically n equal to 2k. K is from 0, 1 to infinity. And then it's 2k and I5 2k. And another case is n is a odd number. K is from 0, 1, 2 to infinity. And basically it's like this. Two cases, because k is from 0 to infinity, it can only be odd number or even number, right? It divide. So for this first term, you can say k from 0 to infinity. This one is 2k factorial, and I time. So this is I 2k, phi 2k. So I 2k is I square k. I square is minus 1k. So basically this guy is minus 1k plus, okay, so let's This is a very simple exercise. Everyone should know. So I did it here for you. Okay. And this one, okay, so k is from 0 to infinity, 2k plus 1 factorial. So I 2k plus 1, 5 2k plus 1, right? So this guy, so I 2k plus 1 equal to I times I 2k. I 2k is minus 1k. So it's I, so this I corresponding to this I, factorial k from 0 to infinity, 2k plus 1 factorial. So minus 1k corresponding to this one, and 5 2k1. So this is nothing but the Tanner series for cosine phi. This is nothing but the Tanner series for sine phi. So get exponential this guy equal this guy. So any question about this part? Yeah, basically the information I want to convey here is whenever you see a function of a complex number and you don't know what's that, you should always ask what's the Tanner series for this thing. You don't need to afraid of this kind of complex functions because it's always defined by this kind of polynomials, the sum of this. And you know each term of this kind of a summation. And yeah, here I just show you some tricks we often use when we prove something. So when you have this kind of a summation from 0 to infinity, and we can do some tricks. Here we divide this kind of into two terms. One is all, one n is odd, and one is n is even. And then simplify them, we get two terms. One is cosine phi, one is sine phi. Versus this is related to the property that cosine phi is an even function and sine phi is odd function. Yeah. Okay, so what else I want to say? Yeah, when we talk about complex series, we can talk about whether this is converged or not, right? Yeah, that's another topic. So basically, basically when we have a complex series, we can always calculate a number. I think you learned in class, like defined by this an plus 1, dn plus 1, divided by an dn. We want this guy to be smaller than 1, then the series is converged. This is also easy to understand because, I mean, very hand-waving argument is like you want your terms be smaller and smaller when you go to infinity, because then you have a hope that it will converge, right? If it's become larger or similar, because you can imagine this kind of a sum as an integral, right? You can, if for the real case, you can when you do a sum is actually similar to an integral. Let's imagine you do an integral function. Of course, you want this integral to be smaller when your x goes to infinity to make the area under this curve to be finite. Right. Yeah, meaning that your value of this function becomes smaller and smaller. Corresponding to the series becomes smaller and smaller for discrete case. Yeah, that's what I want to say about complex numbers. Relative basic. I think in more advanced class, you will learn how to do complex integrals, like the I didn't remember the name, but when there's a pole and you need to do some tricks, counter integral, whatever. Yeah, but basics is important, right? Okay, so let's do some exercise similar to your homework actually. Okay, so you may take a look at the problems. So for example, for the exercise one is for each one you need to figure out the geometric meaning. Let's look at it one by one. So for the first one, if we for z minus 1 plus I equal to 2, you can write z minus 1 minus I, right? Equal to 2. So this guy can be identified as z naught we mentioned before. So basically, z naught is a point in the complex plane, which is 1 minus 1. So this point. And they corresponding to points like on a circle with a radius 2 centered at this point. Right. We can write down the expression for this circle, which is x minus 1 square plus y plus 1 square equal to 2 square, or square root of this guy equal to 2. Any question about this one? Yeah, I guess this one is simple. Let's look at the second one. There's a similar problem in the homework. The geometric meaning is also straightforward. It's all. So basically, um, this this guy corresponding to the distance. So let's assume this point is z. Then the first term, the geometric meaning is the distance from z to the point minus 1. And the second term corresponding to the distance from z to 1. Then the whole thing corresponding to the sum of those two distances equal to 8, which is the an ellipse, right? I think so. And the focus, the distance, sorry, what's the focus distance is 1. We just delta the c equal to 1. And let's draw ellipse, something like this. And of course, you can write down the similarly. So here we write down the equation for this circle, which is s squared minus 1 squared, something like that. So here we can also write down the equation for this ellipse, which is also quite straightforward. Of course, we know the general, by the way, there are two ways to get this equation. So the first way is a smarter way. We can use the, because this is an ellipse, we know that is x squared divided by a squared plus y squared divided by b squared equal to 1. It must be in this form, right? And we also know the c equal to 1. C, what is C? C is given by there's an equation between A, B, C here. So basically A squared equal to B squared plus C squared. This is one property of the ellipse. And this is B squared plus 1. So we can further simplify. Originally, there are two unknown parameters, A and B. now we have only one unknown parameter. So how to fix this unknown parameter B? We notice that there are one condition, one information we didn't use, which is the distance sum is 8. So we need to use that information. Let's just choose a special point on this ellipse. For example, this point, which is easy to write down, because the x is 0. If x 0, then y is b, right? So this point is 0b. So 0b, we can calculate the distance from 0b to this to the point, let's call point A, and also the 0b to the point, let's call point B. By the way, they're the same, right? Because they're symmetric. So the distance, so 8 equal to 2 times the distance, which is given by 1 square plus b square. The distance here is given by, 1 square plus b square, which is the distance. So you can say this is 4. 4 equal to square root of 1 plus b square. So you square both sides, you get this guy, and b square equal to 12. Sorry, not 15. Which you can plug in, you get x squared. A very simple calculation, right? Basically, what you need is this form and this equation and a special point to use the condition that the sum is 8. Of course, you can solve this problem by brute force. You just write down the equation, square root of x plus 1 square plus square root of x minus 1 square plus y square equal to 8. And then do some tricks like square on both sides. Eventually, you will get this equation.
G, I had a
So,
quick question.
sure.
So, how was it that you were able to determine that the focal point or the focal length was 1?
Oh, you
That
mean
C was equal to 1? Yeah.
yeah? I think that's the definition of the focal point, like focus point, like because like we are saying like the distance is from the point Z to those 2 points, and the C corresponding to the distance from this kind of fixed point to the orange, which is 1.
So if you had like instead of Z plus 1 and Z minus 1 in the original problem, there was like Z plus 2, then
Okay.
it just wouldn't be an ellipse anymore.
Okay, if Z plus 2 and Z minus 1, are you saying like this?
Yeah.
Okay, so then you just need to shift the coordinate a little bit to make this number is the opposite of this number, right?
So then it'll be an ellipse still with focal length 1, but it just won't be centered at the origin.
No. So in this case, the focal length is 3/2. Basically, it's the total distance from A to B divided by 2. So here is the 1, here's -1. The total distance is 2. And then divided by 2 is the, so, okay, so let's say if it's like this, very good question. Thanks for asking, like this. Then, of course, there's a -2, there's a 1. Then the ellipse should looks like this. And at this point, the focal length is this distance, which is given by the total distance, which is 1 minus -2, which is 3, divided by 2, which is 3 minus 2. In this case, it's 3/1.
Okay, that makes sense.
Yeah. Basically, you just need to shift the coordinate a little bit and redefine the coordinate. You define the y-axis as like this. I think this is the So you define your A as sorry Z, and your Z prime, your new Z as Z minus 1/2. Then you get something like in terms of the new parameter, you get Z prime. Um, wait, I think some plus 3/2 plus 3 minus 3, something like this. For this, you know how to do it. And once you write down the x square, sorry, x square, a square plus y square, b square equal to 1, then you will know x plus iy equal to, so let's call it prime, equal to x plus iy plus 1/2, x plus 1/2 plus iy. So we know that we just need to replace x prime with x plus this guy, y prime y. So we just replace this guy with x plus. We get the ellipse in terms of the x and the y, original x and y. It's just a coordinate transformation. So you first you start with some kind of a coordinate that is inconvenient. So you choose to you kind of choose a coordinate that is convenient to solve this problem. Then eventually you go back to your original coordinate. Something like that. Okay. Anyway, thanks for asking. It's it's a very good question. Okay, so let's look at the convergence problem. Let's set next problem. So for this kind of convergence problem, it's very straightforward because we know what's the definition of rho. The only thing I want to say is just be careful when you calculate the rho, right? So let's show you, let's say for the first one, we know it's given by 2n plus 1, 3 plus I minus 3. Yeah, by the way, you can take a look at this problem. It's like this. Yeah, here is 2n plus 2 because it's like 2 times n plus 1, then it's 2n plus 2, right? The power here. You can simplify this. This one give us 2. This one give us z plus I minus 3 squared. And this is 2 z plus I minus 3. Yeah. By the way, this equal to this. There's no difference. And also z1, z2 equal to z1, z2. I think so. Yeah. Is that true? Yeah, I think so. Okay, so we want this number to be smaller than 1. Then, by the way, we can erase the this limit because there's no n anymore. So this is z plus I minus 3 squared, smaller than 1/2, and take a square root on both sides like this. So the meaning of this is also simple, also all clear, which is this is z minus 3 minus I. So this corresponding a point at 3 minus 1. and this is a distance, something like this. So basically the series in one only converge within this disk. It does not include the boundary, like the circle is smaller, instead of small equal, it's small. Yeah, for the second part, you can do it similar to what we did here, and just be careful when you do this kind of a limit. Okay, so you can try it. Anyway, I will post the solution after our discussion, so you can try it first and then take a look. So another thing is you need to know how to do this kind of a root, calculate the root. Yeah. Let's start with the first one. We always start with simple examples and then move to more complex examples, because we can always, it's easier for us to understand what's going on in simple example. This is also what we will do when we do research. We always figure out a simple example first, try to understand what's going on, and then apply to more complicated situations. So the first one is like this, the cubic root of -8. So for this kind of problems, we always first we try to write the number under the root as some in this kind of a polar form, right? So -8 is 8 times I pi, exponential I pi, because the -1 is exponential I pi. And yeah, so what's this? This guy can be also written as I2 pi n, because this guy is always 1 for if n is an integer, right? Because it's 2 pi times an integer. It's always it's always 1. So it's 8 exponential I. So it's the 2n plus 1 pi. So this guy is nothing but something like this, right? Which is this. N is an integer. This is 2. So this is, so you can try by yourself. When a equal to 0, the angle is pi over 3, which is what's this? It's like this, right? And when n equal to 2, sorry, n equal to 1 is pi plus 2 pi over 3, which is pi at this point. Oops. And then, by the way, the length is 2. This is pi over 3. This is pi. And when n equal to 2, we get when n equal to 2 is 2 times 2 plus 1, which is 5. 5 pi over 3. What's this? It's I think it's here. Yeah. What if n equal to 3? N equal to 3 is 2 times 3 plus 1, which is what? Which is which is 2 pi plus pi over 3. Then it go back to this point, meaning that there are only 3 different solutions correspond to n equal to 0, n equal to 1, n equal to 2. Yeah. Basically, when you calculate the root of this guy, is equivalent to solve this equation, right? Is equivalent to solve this equation. In general, if this is an nth order polynomial, some number, the number of solutions is always the n here, right? This is like one of the fundamental theorem of polynomials, I think. So you can say because here's 3, this cube equal to -8. We know that there must be 3 solutions, and that corresponds to n equal to 0, 1, 2. And of course, there's a geometric meaning. If you find the first one, then you just divide this circle into equal angle, into 3 pieces, and for each one you get a solution, something like that. But the general approach is like you write this number under the root in terms of like in this form, in this R theta phi form, and then you plus this phi with 2 pi n. Because 2 pi n is always, exponential 2 pi n is always 1, so it doesn't matter. Then you divide by, for example, if you this kind of a number, get this. Oops, I should use another. Then the solution looks like this. And with n equal to 0, 1 to k minus 1. Yeah, something like this. And for the second one, it looks very complicated, but the idea is the same. You write this kind of 2 squared root 3i minus 8 in terms of this polar form, which is I think is something like this. Yeah, I think so. Yeah. Then you know that this exponential can be written as 2 pi n. And then here's the 4. So 4 divided by 4. So this guy is 2. This guy, whatever, you can write it down, which is pi 6 plus n. So n equals 0, 1, 2, 3, corresponding to different solutions. Yeah, that's what I want to say for today's discussion. And yeah, if you have no question, you are free to go. If you have question or something want to discuss, you can stay here and we can discuss.
Quick question.
Sure.
Question number 3, exercise 1.
Uh-huh.
That's only going to be true for exercise 1 is going to be true only for y equals 0, right? Just gives you the x-axis line.
Oh, yeah, right. Yeah. Well, are you saying like can you repeat your question? Just make sure I.
Yeah, exercise 1.
Oh, exercise 1.
Yeah, just the third question. I was just glancing at that and.
Oh well, okay. The exercise 3, question 1.
No, exercise 1, question 3.
Oh, I see. Oh, this one.
Yeah.
I see. Oh, I forgot to do this problem, but yeah. This one, yeah, if you write down z square, which is
You get inconsistent answer unless you let y be 0.
right, which is x. This guy is nothing but x minus 2ix. So you can see the real part always equal. So we only care about the imaginary part, which x, y equal to minus xy, meaning that x, y equal to 0. X, y equal to 0 only when x equal to 0 or y equal to 0, meaning that corresponding to two axes, x-axis and y-axis.
Okay.
Of course, yeah, of course you can solve this problem in polar form. That should be much easier actually. Or okay, both are easy, but yeah, I just want to say that you can also solve it in another. So z equal to r exponential I theta, then this z square becomes r square exponential I 2 theta. This guy, so z bar is r exponential minus theta, right? The square becomes r theta exponential minus this guy. So this guy, they're equal when 2 theta equal to minus 2 theta plus 2 pi n, because 2 pi n really doesn't matter. And this becomes theta equal to, so 4 theta, you move this guy to the left hand side, becomes 4 theta equal to 2 pi n, becomes theta equal to pi over 2 times n. When n equal to 0, give us this branch. N equal to 1, give us this branch. When equal to 2, give us this branch. N equal to 3, give us this branch. Yeah, the match.
Great, thank you.
Any other question?